Let's go over some practice problems that cover things like probability and hypothesis testing. There's lots of practice problems for things like descriptives, going through mean, median, mode, and standard deviation and variance and stuff. So I'm not going to go through some of those, but if you have questions about that stuff, you can always ask. So I figured it'd probably be a good idea to go through talk about probability a little bit, especially this particular problem that I oftentimes will talk about in class as an example. And since we didn't talk about that during the probability lecture, now's a good time to do that. And then we'll go through examples of each of the hypothesis testing approaches. One sample test, the dependent samples test, and the independent samples test, taking sort of one each and showing you the steps, like all the way through an example. So problem number one is oftentimes referred to as the Monty Hall three-door problem, a Monty Hall problem. So here's the setup. A game show host presents you with three doors. Behind one of the doors is a car, and behind the other two are goats or something that you don't want, or just they're empty. Okay. The host knows which door has the car, etc. Right? So it's not like he's unaware. He knows which one has the car, which one has the goats. If you choose the right door, the one with the car, you get to keep the car. However, you don't get to keep the goat if you win one of those. So let's say you choose door number 2. All right, now we can actually see the goats in the car behind there, but let's say you don't see those. And you choose door number 2. So that's the one you pick. I picked door number 2. So you think that's it, right? So I picked door number 2, and you might be asking yourself or thinking about this in terms of probability. What's the probability if I'm talking about 3 doors? Let's do it here. So I have door number 1, okay, door number 2, and I have door number 3. So again, forget this picture back here. Let's just say that you pick as a contestant, you pick door number 2. And again, you think you're done. And when you pick door number 2, you're probably thinking, all right, well, what's the chance? What's the likelihood, the probability that I picked the correct door? That the car is behind the door that I chose? Well, you likely have a sort of 1/3 chance, a 1 in 3 chance of picking the correct door. That's right, there's 3 doors, you pick one of them. So there's a 1 in 3 chance you pick the correct door. But to make things more interesting, before what is behind door number 2 is revealed to you, the host says, well, all right, so you picked door number 2. I just want to tell you that for sure the car is not behind door number 1. So the host will remove a door, let's say, show you the goat or whatever is behind the door. So you're left with these 2 doors, door 2 and door 3. The host will then ask you, do you want to keep your original choice of door number 2, or would you like to switch to the other remaining door, door number 3? And the question comes down to, should you keep the door, keep the choice you made, or should you switch? And the bigger question is, why should you switch? So the way this oftentimes plays out, and people's sort of thought process about this is, I'll do this in a different color, I'll do this in pink, is that when this door gets, so at first you realize that there are 3 doors, so your original choice is that there's a 1 in 3 chance. So psychologically, when this door gets eliminated, our minds automatically assume that now there is a 1 out of 2 and a 1 out of 2 choice, right? They were down to halves, right? 1 door got eliminated. I keep saying eliminated, and you're down to 2 doors. So your original choice now, that was originally 1 out of 3, has now become a 1 out of 2. The other door is a 1 out of 2. So in our minds, we think it doesn't really matter if I stay with the door that I chose or if I switch to the other door, because they both have about an equal chance of having the car. But there's a problem with that sort of thought process. Again, it comes down to the fact that you don't know where the car is. You don't know anything behind the door. So when you do choose, your original choice is 1 and 3. And even when this door gets eliminated, this 1 out of 3 chance that you originally have doesn't change. You still chose the door with a 1 in 3 chance of having the car. That doesn't change. So even though it feels like it goes to 1/2 and 1/2, it doesn't. Okay? You actually still have a 1 1/3 chance of picking the right door. All right, so if picking the right door had a 1 1/3 chance, that means combined, these two doors, right, had a 2 out of 3 chance. Right, originally, 2 out of 3 chance, because you had a 1 out of 3 chance of being correct. The other two doors collectively had a 1/3 and a 1/3, so together they're 2 out of 3. When I eliminate this door, or when the host eliminates this door, that 1/3 that goes to this door doesn't just go away. It doesn't disappear. It just doesn't, it's just no longer behind this door anymore. And because the car's definitely not there, there's a goat there or whatever else, its probability just gets transferred over to the other door. So your door still has a 1 out of 3 chance, but now all of a sudden the other door doesn't have a 1 out of 2 and a 1 out of 2. It actually has a 2 out of 3 chance of being correct. Now you still may be in disbelief about this, that there's no way that's true. If you have 2 doors, it's still 1/2, 1/2. This came about, the reason why this particular problem came up is there's a game show called Let's Make a Deal. It's come back around. It's now, I think, hosted by Wayne Brady or something. But originally they had this thing. This was like one of the big prize things, was you were confronted with these 3 doors, and this sort of, it preyed upon people's general psychology, which is that once we make a choice, we tend to stick to it. It's very difficult for people wanting to give up a choice and or change their mind, because there's so much that goes into making a choice. When you finally make it, it's very hard. So, for instance, we put a lot of thought and rationalization behind why our choice was the right choice. This goes for a lot of things. If you applied to many universities and got in a few or whatever, and when you decided to go to CSUN or wherever it is you decided to go, once you decide, you make that decision to go to a location like like CSUN versus other schools, you start to rationalize why that was the best decision, to support that the decision was the correct one. And you start to come up with all kinds of reasons why your choice was the best. This goes when we're dating, this goes with all kinds of different things. As soon as we make a choice about something, we tend to try to psychologically support that. So when you make a choice to pick door number 2, most people tend not to want to switch. They will stick to their original choice. And what they found when people actually studied the game is that it seemed like people that stayed with their choice lost more often. By that I mean they did not win the car. And people that switched, those that actually did decide, okay, fine, I'll switch to the other door, they won a lot more often. And somebody actually started keeping track of this and noticed that there was this 2-to-1 sort of ratio, that people that switched actually won twice as often as those that stayed. And they'd simulated this and done all kinds of stuff with this. Actually ends up being the case, that the 1/3 that you originally had when you picked the door stays the same. The 2/3 that covers the other 2 doors doesn't go away. It's just as this one gets eliminated, that 1/3 gets transferred over to this door, so that your original door still has 1/3, but the other door now has a 2/3 chance of being selected. So this is where probability starts to get complicated, because sometimes the probability or likelihood or chances that things occur can go against what seems makes sense. It goes against our sort of better judgment. It feels like by getting rid of a door, we have 2 doors left, so the probability is really just 1 out of 2 for each of them, but that in fact is not truly what happens. If you look up the Monty Hall or a 3-door problem or 3-door probability problem, you'll see lots and lots of people that talk about this, and they'll give you the same or similar sort of rationales about how when a door gets removed, again, because the host knows there's no car there, that the probability that was behind that door gets transferred to the other remaining door or doors. So to illustrate this more, think about this for a second. What if we had more doors? What if instead we had 7 doors? Same basic setup, we have 7 different doors now. All right. You pick door number 3. So you decide just to number these, and we can use a different color. What would stand out? Let's see, maybe this is door, here's, door number 1, this is 2, this is 3, 4, 5, 6, and 7. Okay, so you have 7 doors. You pick door number 3. So door number 3 is the one that you decide to choose. Okay, so this is your pick. Okay, so there's your pick. And everyone right away can, the one part of this that no one sort of disagrees upon or whatever is that your first choice, right, by picking one of the doors, your first choice, really, there is a 1 in 7 chance that you pick the right door. So to begin with, there are 7 doors, you pick one of them, so it's a 1 in 7 chance. Seems pretty straightforward. The host opens doors 1, so that's gone. 2, that's gone. And 6 and 7. Okay, so those doors have now been opened, and you can see there's a goat behind them, or it's empty, or whatever they have there to indicate there's no car. Right? You haven't won a car, or that the cars aren't behind those doors. Let's actually do this a little bit easier, even. So let's say that this is different than what's said here. Let's say he also gets rid of door number 5. So you're left with your door that you chose, and the other door is door number 4. So unlike the 3-door problem, hopefully your internal sort of voice should be telling you that this seems different. So if you're asked if you want to stick with your door or switch to door number 4, people oftentimes, because there's more doors, they're now more compelled. I mean, imagine 100 doors. Okay, you can go further. If 100 doors, you pick door number 55. They get rid of all but door 55 and 56, so you're left with just your door and 56. They get rid of 98 other doors. These other doors are getting closed off, and you're down to your door and one other door. It all of a sudden feels a lot more compelling that you should switch, right? Because all these other doors don't have the car, and they're being all the way down to just your door, the one you had a 1 out of 50 to choose, or in this case 1 out of 7, and then the remaining door. This feels a lot more like all the other probability from these other doors are being placed behind this door. So if the original choice doesn't change, you have a 1 in 7 chance out of picking this one door, well, then for it to be door number 4, if there's only one door left, right, and you're being asked if you want to stay or to switch to door number 4, well, what's the probability it's behind door number 4? Well, if you have a 1/7 chance of being correct the first time, and a 6/7 that was behind one of the other 6 doors, well, all that other probability gets put behind door number 4. So you end up having a 6/7 chance if you choose. You're 6 times more likely to win if you switch to this remaining door than if you stick to your original door. So all the other probabilities from the doors that got closed are all being piled behind the one remaining door that you didn't choose. Now, if you stay, you still can win. It's likely you picked the right door to begin with, but you only have a 1 in 7 chance. But if you switch, you have a 6/7 chance. So, okay, so let's go back to the problem the way it's written. Hopefully this seems more compelling, that it's not just, all of a sudden, this doesn't feel like it's 1/2 and 1/2, right? It doesn't feel like that anymore. Well, let's go back to the original problem, as stated here. you chose door number 3. Get rid of all the doors except for 4 and 5. So you're left with your choice, door number 3, and doors 4 and 5. So you have a 1/7 chance of being correct. And before any of those doors got closed, it's fairly obvious to figure out that you have a 6/7 chance of being wrong, right? All right, so 1/7 chance that you picked the right door, but there's 1, 2, 3, 4, 5, 6 doors. So you have a 6/7 chance of being incorrect. As each of the doors gets closed, there's 1/7, another 7th, another 7th, another 7th. All those 7ths get piled up. So because I have a 1/7 chance of being correct, a 6/7 chance of being wrong, all those other choices are being sort of piled up behind the other 2 doors. So combined, the 2 of these doors combined, this door and that door, right, together, collectively, have a 6/7 chance of having the car. Your door still has 1/7. Doors 4 and 5 have 6/7 together. So it says you now have a choice to stay or switch to either door 4 or door 5. Now notice you can't pick both 4 and 5. You got to pick one or the other. So should you stick with your door or pick one of 4 or 5? And the answer is, well, because the 2 doors together have a 6/7, that means that door number 4 has half of that, which is 3/7. The other door, door number 5, has the other 3/7. So each of these doors, 4 and 5, have a 3/7 chance of having the car, where your door only has a 1/7 chance. So if you switch to door 4 or door 5, you're tripling the likelihood that you actually will be able to win the car. So even if it's split between 2 doors, each of those doors still has a higher likelihood of containing the car than yours does. So you might as well switch to one of those. Okay? Sense? So the reason why, if you stay, you have a much lower probability. If you switch to one of the other doors, now which one you choose, 4 or 5, it's up to you. But each of those doors has a higher likelihood of having the car because the other doors were eliminated. And again, those definitely did not have the car behind them because the host knows where it is. You now are faced with a 1/7 versus a 3/7 choice between doors 4 and 5. Still makes a lot more sense to change than it does to stay because you have a much higher likelihood of finding the car behind 4 or 5 than you do behind your one door that has a 1/7 chance. All right. Again, this is to illustrate that sometimes the way that probability works out doesn't always seem intuitive. It sometimes can be go very much against our intuition about how the probabilities are supposed to work. It seems like if you get rid of all these other doors, you may still be arguing, well, you're down to 3 doors, so now we're back to having a 1/3, 1/3, 1/3 chance. And that's just not how it works out. This has been simulated multiple times. If you switch, you're more likely to win, 3 times more likely to win than if you actually stay with the original door, switching to either of those doors. All right. Hopefully that's clear. And even if it's not clear, and if you still don't believe it, if you're like, no, my gut's telling me that it's wrong. Again, look at it. Do some exploration. To go to to Google or some other search engine and just look up the Monty Hall door problem or the 3-door problem, and look for some other explanations. You'll see that what people have figured out is that as the doors are being eliminated, those probabilities are actually being placed behind the remaining doors, and the likelihood sort of works out. It doesn't go away. It doesn't all of a sudden go from 1/7 and 6/7 to being 1/3, 1/3, 1/3. Because the original setup of 7 doors is still guiding the probabilities. Doesn't just go away. Those other 7ths are going someplace, and it turns out they're going behind the remaining doors that are actually still in play when a person's choosing. And if you're even more interested, if this is something interests you, there is on Canvas there's a folder for syntax, and one of the SPSS syntax in there is the Monty Hall problem. And what that does when you run it, it actually does simulate this exact process, this process, but it does so like 1,000 times or 10,000 times, some large number of times. If you run the syntax, it'll then spit back to you output of the likelihood of winning if you switch versus stay. And you'll see that you're 3 times more likely to, or twice as likely to, no, 3. 2/3 there's 1 to 2 times more likely to win if you switch than if you stay, and it actually simulates that process a bunch of times. So something, if you're interested in it, it's there, you can run it. Something we used to do as part of the lab, but there was too many sort of issues to sort of to do that in lab, so it got taken off. And you might notice too that the labs go, I think it goes lab 4 to lab 6, because that used to be a big part of lab 5, and we stopped doing lab 5. And that's why it goes 4 to 6.